Good day, everyone. Thank you for joining us today at the eBPF Summit 2024. My name is Vamsi Kalapala, and I'm joined by my colleague, Anubhab Majumdar. We are excited to share our insights on enhancing efficiency and visibility, optimizing eBPF programs for advanced observability. This session will delve into how we can design more efficient and scalable eBPF programs for network traffic observability. To give you a brief overview of what we will be covering today, we will start with an introduction to the problem space and provide some context around network observability challenges in Kubernetes environments. We will then discuss potential solutions. Let's begin with a bit of background. Our work is part of the Microsoft Retina project, an open source eBPF-based Kubernetes network observability platform. Retina is a lightweight solution designed for continuous monitoring. Traditional monitoring solutions often struggle to keep up with the dynamic nature and volume of network traffic in Kubernetes clusters. This is where eBPF comes in, offering a powerful way to monitor network traffic at a granular level. As we dive deep into the problem, it becomes evident that continuous network monitoring in Kubernetes clusters is no easy task. The first challenge is event volume. In a large-scale cluster, the amount of network traffic is immense, and observing every packet can quickly become overwhelming. This leads to the issue of resource footprint. How can we monitor such a high volume of events without consuming excessive computational resources? Another critical challenge is data accuracy. In an environment where thousands of events are generated every second, ensuring that the information collected is accurate and actionable is paramount. Lastly, there's the overhead on data path latency on customer workloads. eBPF programs, while powerful, can introduce significant latency, particularly when they are not optimized. This added latency overall performance of the network, which is something we must carefully manage. The challenge here is to achieve accurate network event information at scale without sacrificing performance and efficiency. So given the challenges we have just outlined, the key question is, how can we optimize network observability in Kubernetes clusters without overwhelming our resources? First, we need to critically assess whether we truly need to capture all the events. Often the answer is no. Capturing every single event can lead to excessive cost, resource consumption without delivering proportional benefits. Instead, we should focus on event relevance, prioritizing events that would provide actionable insights and disregard the rest. Another important consideration is the application context. Users generally care about monitoring specific namespaces and pods rather than the entire cluster. Not all packets are equally important, and the key is to identify which ones are critical to the user's needs. Furthermore, it's crucial to ask, can we selectively monitor only the pods that are of interest to the users? By doing so, we can significantly reduce the volume of data we process, making our eBPF programs more efficient while still delivering the visibility required. With that, I'll pass it over to Anubhab, who will talk you through the specific solutions we have developed to tackle these issues.
Thank you, Vamsi. The first solution we implemented is pretty rudimentary. We allow users to annotate namespaces and/or pods that are of interest to them and record the IPs of those pods in an eBPF map. The eBPF program is modified to match the source and destination IP of each packet it sees against the map to determine if the packet is of interest to the user. If you're interested in only a small subset of pods, this solution works great. But the disadvantage is it doesn't provide monitoring of the entire cluster, which is one of the most potent features of continuous monitoring. Moreover, if user annotates all namespaces, it negates all advantage this approach provides. The second solution that we implemented is based on the principle that not all packets flowing through a node are equally important. Rather, a small subset of them provide actual useful signal. For example, in a long-running TCP UDP or UDP connection, user cares about when the connection is established and how long the connection is alive. They do not care about signals for every data or acknowledgement packets flowing through the node as part of the connection. This allows us to sample packets rather than reporting every packet encountered by the eBPF program. This slide provides a very simplified version of the algorithm we use to determine the packets of importance. To do this, we maintain a list of recently seen unique source destination IP port pair. For every packet, we check against the list to see if the connection is new. If yes, we report it immediately. Otherwise, we only report data or acknowledgement packets every 30 seconds. The list is curtailed when we encounter a finish flag or after a certain amount of time. The big advantage that we can provide is we can provide continuous monitoring for all pods in the cluster and not a subset of them. This also reduces the network latency because we write very small number of events to the perf array, and that is the most costly operation that adds to network latency. One downside of sampling is if we want to accurately measure the amount of bytes a pod receives or a pod sends, and we want to do this calculation in the user space, we cannot do that anymore because we are sampling at a kernel level. So how much does this enhancement that we discussed improve performance? This slide shows the advantage of sampling when reducing missed events from kernel. To create a baseline, we set up a cluster running ping mesh pods, installed Retina without filter map or sampling enabled, and ran it for 30 minutes. During this period, we counted the number of events that got overwritten in the perf array because the user space program couldn't read them fast enough. The light blue line shows the result. In the same cluster, running the same number of pods, when Retina is installed with sampling enabled, we can filter out almost 90% of packets seen in the node without missing any new connection established by a pod in the node or to a pod in the node. Sampling can even outperform filter map-based approach, where we observe only a third of the pods running in the cluster. Similar benefits can be seen when measuring network latency introduced by eBPF programs. We used iPerf and NetPerf tools to measure throughput and mean network latency respectively for both intra and inter-node traffic. Baseline is established on a Kubernetes cluster without Retina installed. The graph on the left shows transaction rate, while the graph on the right shows TCP round-trip latency. To establish the worst performance, we installed Retina without any of the enhancements discussed. We impact throughput and latency quite significantly. For example, Retina without any improvement can add almost 10 microseconds to mean latency in intra-node pod-to-pod TCP communication. Next, we installed Retina on the same cluster with sampling enabled. By leveraging sampling, Retina introduces slight to no latency in both throughput and TCP round-trip time. For example, Retina introduces only a 2 microseconds to mean latency in intranode pod-to-pod TCP communication. In conclusion, we saw that by using sampling in eBPF programs, we can provide key metrics continuously without sacrificing performance or breaking the bank. Some enhancements that we want to make in future iteration of Retina is to provide an accurate measure of bytes each pod receives or sends, or the total amount of bytes flowing through a node. Allow eBPF programs to behave differently to adapt to change in traffic pattern, and allow users advanced control over eBPF program behavior to fit their own use cases. That concludes our presentation. Thank you so much for listening to us. Thank you.